Hello everyone, I'm Yogi Singh. Welcome to my YouTube channel, Yogi's Data Lab. Today we are going to cover a case study on linear regression. We just saw in the previous video the theory of linear regression, and we are now going to solve a problem statement where we are trying to predict the price of home using a couple of features that have been given. So as you can see on the screen, the data that has been given is the price of the house, which is my target variable. I have area of the house, number of bedrooms, number of bathrooms, number of floors. Is the property situated on the main road? Does the house have a guest room? Does the house have a basement? Does the house have hot water heating? Does the house have air conditioning? Number of parkings available. Is the property in the preferred area, and the type of furnishing of the house, whether it is furnished or unfurnished. So my target variable is price, and all the other variables are going to contribute towards the price of home. So let's start. So I'm going to import my packages. I'm importing NumPy, Pandas, Matplotlib, and C1, which are the basic packages, which you already know. I'm importing train test split, which is going to be used to split the data. I'm using linear regression from Scikit-learn. I'll also use SM from Statsmodel. So we are going to do linear regression in two different ways using Statsmodel as well as Scikit-learn. I'm importing the matrix R square mean squared error over here. I'm using variance inflation factor and het white. Variance inflation factor will be used to remove multicollinearity, and this het white will be used to do the test of homoscedasticity, which is one of the assumptions of linear regression. So I'm reading my file. I create a copy of my file and I do a head. When I look at the head of my data, I see that I have price, which is in a very high scale. Other than that, I have a couple of numerical columns and I have a lot of categorical columns. But it is okay. The data seems to be clean. My column names are clean, so it is good to proceed. Let's go ahead. When I do a shape, it shows me I have 445 rows and I have 13 columns in my data set. When I look at the info, it shows I don't have any missing values. I have 6 integer and 7 object columns. I'm checking for the missing values. I don't have any missing values. I don't have any duplicates. So this is all good. Now we will start with the basic EDA, or the exploratory data analysis of these variables. So let's start with the univariate analysis. I'll start with the numerical column, which is area. When you look at the area column, the histogram of it, it shows that there is a skewness towards the right. When I look at the box plot, I do see a couple of outliers over here. Now, we can say that the data is skewed towards the right and has a couple of outliers. And we'll leave the values as of now without capping them, because they can, they actually look like actual variables. Some houses can have larger areas. So I'm going to leave it as it is. We'll see later on how it is performing, how it is impacting my results. If I'm not getting good results, maybe I'll try to cap it and check exactly how things are working. But for now, we'll leave it as it is. Now, parking column. When I look at the parkings, I see most of the houses don't have parking, while a very few houses do have 3 parkings as well. We will try to do a group by of parking to calculate the mean of price. Now, the purpose why we are doing this is, if you look at the distribution of the data in parking here, 3 is a very small amount, see? So statistically, the contribution can be very less in this part. So maybe, is it possible that can I merge 3 parking with any of these values? If I can, but before I merge them, I need to check it statistically if the contribution towards the target variable is similar for any of the other values, which is for 3 parking as well. So when we are looking at this, when I'm looking at the mean price of homes, what do I see? I see that for 3 parking, it is 5.86 into 10 to the power 6. This is 5.89 into 10 to the power 6 for 2. So approximately, I can say that they are very close by. So possible that I can replace 3 with 2. So what we are doing, I am replacing the value 3 with 2 for parking. When I replace this, now you'll see that the distribution that I have for 0, 1 and 2 is decent, and this very small quantity of 3 parking has been merged with 2. Fine. Let's look at the other ones. I'm talking about the number of bedrooms. So I see most of the homes have 3 bedrooms followed by 2 and 4. There are very less homes or houses with 1 bedroom and 6 bedrooms. Fine. So again, we'll follow the same process which we did for parking. And I'm going to look at the bedrooms, and I'm going to take the mean of the price. Now, if you look at this closely, this is not very close, but approximately I can say 6 and 3 are statistically contributing nearly same towards the mean price, while 5 and 4 are approximately contributing very similar. However, with 2 bedrooms and 1 bedroom, the prices are very different. So we are going to leave them alone. Now, let's have a look. So what we are doing here is, wherever it is 6, I am replacing that with 3, and wherever it is 5, I am replacing that with 4. So what will happen is, this value of 6 bedrooms gets merged with the maximum values of 3, and this value of 5 gets merged with 4 bedrooms. So this is what we have done. One has just 2 records, which is fine. I didn't merge it because if you look at this, the contribution is very low as compared to the other values. Hence, we are leaving it alone. Let's look at stories column, which is the number of floors. So when you look into the stories column, you see that most of them are 1 story or 2 stories. 3 and 4 are less, but they are still some values. So we'll leave them as it is. Main road, let's look at main road. When I look at the count plot of main road, it shows that most of the properties are on the main road. Very few properties are not on the main road. When you look at guest room, most of the homes don't have guest room, while a few of them have. When you look at basement, most of the houses don't have basement, while a few of them do have basements. Hot watering, majority of the houses don't have hot watering. Very few of them have hot watering. When you look at air conditioning, most of them don't have air conditioning. Few of them have air conditioning. Okay. Parking 0, 1 and 2. This we have just merged. So we can go with this. And it shows that most of the house don't have parking even. When you look at preferred area, majority of the properties are not on the preferred area, while few of them are on the preferred area. Furnishing status. So most of the homes are semi-furnished, followed by unfurnished, and then furnished. Means furnished homes are the least amongst the homes that we have for the furnishing status. So we just completed the EDA, and now we can start building a model. So the first model that we are going to build is using all the columns as they are, and we'll use Scikit-learn to build the model. So how do we build it? So these are a couple of steps that we need to do. The first thing that I'm doing is I'm preparing my independent data set and my dependent data set. So price was my dependent variable. I dropped price from the data frame and I prepared my independent data set. The price column, I'm putting it in my dependent data set. So I have two values here, xorg and yorg. Xorg will be having all the independent variables and y will have the dependent variable. Now, if you noticed, we had categorical columns in a data set. We had string values, right? Now I am going to build a mathematical model, so I cannot go ahead with the string values. So I have to convert them into numbers, and hence I am creating dummy variables by using one hot encoding. Now, how do you do that? I have used pt.getDummies. I have given my independent data set. I have said select my object columns, drop first equal to true, and d type int, where because if you don't give d type int, you will end up getting true and false. So I have given int, I'll get ones and zeros. Once I've done this, I see that all my dummy variables are created over here. So my data is ready. My independent data set and my dependent data set, all of them have become numeric now. And I will go ahead and split the data into train and test. So let's split it. Now, when I'm splitting the data into train and test, I have used 30% of my data, which goes into the test, and 70% of my data, which goes into the train. I'm also using random state. Random state is more like setting the seed. The reason why I'm using random state is because whenever you split the data, every time it does a random sampling. So it is highly possible that any record which went into your train set in the next iteration when you are running it could possibly go in the test set, and anything which was in the test set could possibly go in your train set. Now, because of the shuffling of the data which can happen every time you run, the results will keep on varying slightly. I don't want that to happen, and hence I am fixing that anyone who is running this code with the random state that I have set, the records which went into train for me also goes into train for the same person, and the records which went into test for me also goes into test for the same person. So this is known as setting the seed. So I have uploaded this code and the data file on GitHub. Whenever you download this and you're running this, if you do not change the value of random state, you will also get the same results as I have got. In case you change the random state, you might get different results, and random state equal to 1 is not the fixed value of 1 that I always have to get. I can give this value as 42, 2, 5, 15, whichever number I want, but just ensure that whenever you are running this code, the number doesn't change. That's random state. So I see that I have gone ahead and split my data into train and test. And now I will build the model. So building the model, I have done linear regression and I have created an object here and lr underscore org.fit on the train set. And this is what is the model. That's it. Now, if you look at the intercept, it shows that the intercept is 84,244.48. And the coefficients, which means this was your beta 0 intercept, beta 1, beta 2, beta 3, beta 4, and likewise, you'll have all your betas over here. So this is what I have got, and I am building the equation of linear regression. This is the code to build the equation, and you can see that my target variable price, which is y, is equal to 84,244.49 plus 247.14 multiplied by area plus 31,012.87 multiplied by bedrooms. And like this is the entire equation that will give you the price. So this is the equation of linear regression, which was formed using Scikit-learn. Fine. Now, since I have the equation with me, I can now use this equation to predict it on the train set as well as on the test set. So what I am doing lrorg.predict. lrorg is what? That is my model. Model.predict on the train set and model.predict on the test set. So the purpose of me predicting on both the train set and the test set is to identify whether my model is overfitting or not and what are the results of my model. So the matrix we already know, R square, RMSE. Here I am not getting into all the matrix. Here we'll be comparing only the R square and RMSE. So I'm checking R square, where I'm giving my original Y variable and the predicted variable, which we just predicted here. It gives me the R square of the original data. I am giving the R square for my test set now. and it gives me the test R square. If you look at this, I am getting 68% R square on my train set and 67% R square on my test set approximately. So the difference between the train and test is less than 2%. One is 68%, another is approximately 67%. So they are very close by, and since they are close by, I can say that the model is not overfitting. The results are also okay. They are decent. They are not very highly performing, but they are not very poor either. So 68, 70, 72% is a decent R square, which we can accept. Here with 68 and 67%, I see that the gap is less and they're very close to 70. So I'm giving a good model. Now, when I check for the RMSE, so I've calculated the mean squared error and I've taken a square root of that. When I calculate the RMSE, I see that it is very huge, right? It is somewhere around 1 million. This is 1.16 million. So if I'm getting such a decent R square, why is my RMSE so high? So what is RMSE? RMSE is going to be calculated based on your output variable. So if you look at your output variable Y, you will notice that the scale of your Y was huge. Let's see. The scale of Y was huge. So if I'm doing this minus some value, it's obviously going to be very huge. So the next step that we are going to do is we are going to look into a situation. How do we handle this data, or how do we solve this problem if my target variable is having a high scale, such that when my R square is good, my RMSE also should show that it is a lower value and I should get decent results. Overall, the Scikit-learn model that we built with the original target variable, the R square, is good. The RMSE seems to be very high and I cannot compare them. So let's go ahead and see what we should be doing. Now, let us look at model 2. So here what we have done is we have normalized the target variable. So when I normalize the target variable, what will happen is the scale will reduce. Rest everything remains the same. I have just normalized the target variable. So let's look how we do this. So I have taken a log of the target variable, which is price, and I've created a new column called log price. The log price is the normalized variable of the price column, and I can go ahead and drop the price column now because I'm going to use the normalized variable, which is log price. Now, since I have my new target variable, which is log price, I'll again repeat the same steps of creating my independent and dependent data set, creating my dummies, and splitting my data into train and test. Now I will go ahead and build a linear regression model, the same way which we did above, just that I have changed the target variable from the original target variable to a normalized target variable. Now, when you look into the results, I have built my linear regression. I have calculated my intercept. You see the values have reduced. When you look at the coefficients, it is no more than thousands. These are small numbers now. They are all decimals. So this is the impact of converting your target variable, which was very huge, to a small value. Now, when I go ahead and look at the formula, if you look at this, 14.35 plus 0 multiplied by area plus 0.01 multiplied by bedroom plus 0.18 multiplied by bathroom. So this is what I am getting. I'll use this to predict on my log train and log test. Let's have a look at the R square. You see the R square that I'm getting now is approximately 71% on the train set and 67% on the test set. So this is the prediction on the train and test, and I am getting R square, which has improved even from what I was getting on the base variable. And if I look at RMSE, you see the differences have become comparable. It was for train, it is 0.20 now approximately, and this is 0.23. So this becomes more comparable as compared to what we were getting before. So the purpose here of me scaling the data and first running it normally was to understand that if I'm getting a decent R square, my RMSE should also be comparable. So if you have a large scale of your target variable, what you should do is you should go ahead and normalize it and then build your model with the normalized new target variable as your target variable. Now this was with sklearn or scikit-learn. We are going to rebuild this model with Statsmodel, and we are going to check which one of them is performing better. Is the Statsmodel giving me better result, or is it the sklearn model which is giving me better results? So let's have a look. So to build a Statsmodel, we will add a constant. We have to add a constant because the algorithm doesn't have the provision to give you an intercept which is beta 0. If you don't get a beta 0, all the lines will pass through the origin, right? Because that is the intercept. An intercept is what? It intersects your y-axis when x is equal to 0. If this is not there, everything will start passing from the origin. And if everything starts passing from the origin, the intercept will not be able to adjust to the error. So the purpose of an intercept is that if I have certain points here, rather than having a line going like this, I should move it slightly up such that I have a better adjustment to the points. So if the intercept is not added, then the errors will be more and the results will be skewed. Skewed as in not perfect. So here we need to add a constant. The constant will do nothing, but it will add a column const and add once over here. Sometimes you get into trouble that this add constant doesn't work. So if that is not working, go ahead and create a column called const and put values 1 over here. That's all you need to do. So I'm adding the constant in both the train and the test set. And I'm using Statsmodel now. Earlier I was using sklearn, now I'm using Statsmodel. And I'm doing statsmodel.ols. And I'm going ahead and training my model over here using .fit. After I've done this, I'll print the summary. When I print the summary, I see that I'm getting R square of 70% and or 70.5%, and I adjusted R square of 69.5%. I see I have my constant, my area, and I have all my beta coefficients. These are all my beta coefficients. These are my x's and these are my p-values. So you don't need to go ahead and look at everything in this table. You don't require. I'll just tell you what you need to look at. So you need to look at these two things that they should be close by. You need to look at this, which is your x variables. You need to look at this, which are your beta coefficients. And you need to look at this, which are the p-values. Other than that, you don't need to look at anything in this table to determine how your model is performing. So what we are going to do now is, let's proceed, we'll see. So what we are doing now is, once I build the model, I'll check for multicollinearity. So this is a function I've written for calculating the VIF, and we'll calculate the VIF. The constant, you should not be bothered because this is just a constant term, so it doesn't matter. It can have any value, just forget it. Look at all the other variables. They should not be above 5. So 5 is the threshold which we are taking here. So we discussed about it in the theory video. If you have not looked at it, go back and have a look, where we talked about using a VIF of 2, VIF of 5, when to use what. But here we are taking a threshold of 5 and all my variables are below the value of 5. Since all the variables here are below the value of 5, it means that I don't have any multicollinear variables. So if I don't have multicollinear variables, which is good, multicollinearity, just to help you recall, it means the impact of one independent variable on the other independent variable. If one independent variable changes by 1 unit, what is the impact of it on the other independent variable? If it changes multi-folds or multi-times, that is what is multicollinearity, and we measure it using variance inflation factor. So here we see that none of the variables have a VIF greater than 5, which means that the model is performing well. Well, good. No multicollinear variable, so I'll go ahead and do the significance test. Now, what is significance test? In significance test, what we do is, I told you just now, a few minutes back, that we'll look at the p-value. So what we do is we remove any variable whose p-value is greater than 0.05. Now the question is, why do I do this? So let's understand this. It is known as a significance test. We'll first write the null hypothesis and the alternate hypothesis, and then we'll talk about it. Okay, so this is the significance test. Whenever we are testing anything, we have a research hypothesis, we want to know about it, we put that in the alternate because that is what we are testing. So what am I testing here? I am testing whether any of these variables that I have, they are significant towards my target variable, or is stories significant towards the price? Is main road, yes, significant towards the price? I want to check that. So what I'm testing here is that, let's say, is stories significant towards my target variable price? So since I'm testing this, since I'm checking that this variable is significant towards this variable, towards my target variable, so my alternate hypothesis becomes X is significant towards Y. So null is what? Null is the complement of your alternate, which means X is insignificant towards Y. So if my p-value is greater than 0.05, what do? We fail to reject the null hypothesis. So if I fail to reject the null hypothesis in this case, it means that the X is insignificant towards Y. So if X is insignificant towards Y, it means that that X variable is not contributing towards the Y variable. And if it is not contributing towards the Y variable, it means I can go ahead and drop that variable from the model. So how do we do that is we'll pick one variable at a time. Always remember, you are not supposed to drop multiple variables together. You are going to lose important variables. So what we are going to do is I am going to drop one variable at a time. But which variable to pick first? We'll go ahead and pick up the variable which has the highest p-value, drop it, again build the model and check the summary, pick up the highest p-value. If it is greater than 0.05, drop it, build the model, check the summary, and repeat this process until all your variables are less than 0.05. So let's have a look. We have written a function for that. So this is the function where it is going to pick up the p-values, pick up which is greater than 0.05. You see, if it is greater than 0.05 threshold, which is 0.05, it is going to drop that variable from the model. Otherwise, it will continue. So having done this, we have picked up the model and significant variables by using this function. So these are the list of all your variables. These are the final variables which are significant. Now, it also has told you which variables it has removed, you see. And now we have built the model. And when I look at this p-value column, I see that all my values over here are less than 0.05. It means that I don't have any multicollinear variables and I don't have any insignificant variables. Now, since I don't have any multicollinear or any insignificant variables, it means that my stats model is complete and I have created my final model. I can go ahead and look at the R square and the RMSE for this model now. So let's check it. So I'm filtering out the data for significant variables. And now I'm building my model. So this is the final regression model that you are getting, or the formula. Let's check the results. So I predicted on my train set and my test set. And I see that my R square is 70% on the train and 67% on the test. When you look at the RMSE, the RMSE is 20% and 23 approximately. So what do you see here is that your Scikit-learn model or the Scikit-learn model, which I did in a single line of code using linear regression, is giving a similar result which we do using stats model by removing multicollinearity and even by removing insignificant variables. So either you use sklearn or you use stats model, you are going to get similar results. Now, so we saw that we have built three models till now. One, we built sklearn model with the original target variable. We built sklearn model with the normalized target variable. We built stats model with the normalized target variable, and we saw that sklearn with the normalized target variable and stats model with the normalized target variable are giving me similar results. As I have always emphasized on feature engineering, we are going to do some feature engineering now, and we are going to look at the results of the model. So we'll now stick to sklearn model. We already know that stats model, sklearn model is giving me the similar result. So we'll stick to sklearn model, and we will build the sklearn model after doing some feature engineering. So let us start with that. Now, when we are building this model for going ahead with feature engineering, what I've done here is I have gone ahead and run a chi-square test to determine which of these categorical variables are dependent on each other. So if the categorical variables are dependent on each other, it will help me to create some features because of the dependency on each other. So here is what I'm doing. I'm creating a contingency table of the categorical variables, and I'm performing a chi-square contingency, giving that contingency table here. So it returns me the p-value, and from this I have given the categorical columns, and I have called the chi-squared dependency function, and it tells me which of these variables are dependent and which are independent. I've filtered out all my dependent columns, and it shows me that furnishing status is dependent with main road, guest room, basement, air conditioning, preferred area. Main road is dependent with guest room, air conditioning, and preferred area. Guest room has something, and so on. So I know that these are the pairs which I can use to create my features for feature engineering. So what we have done here is I have created a couple of features. So the first I have created is interaction variables. So the first one that is created is that furnished houses on main roads might be more desirable by the buyers. So what we have done is we have created a column called df furnishing underscore main road. So if it is a yes, so I've gone ahead with yes underscore yes. Okay, so this is how I've created these variables, or 1 underscore 1, 1 underscore 0. Then the other is houses with main roads in preferred areas could attract premium prices. A house with both a guest room and a basement might appeal to buyers seeking spacious properties. Air-conditioned houses in preferred areas might fetch higher demand in warm climates, and a guest room in a preferred area could be marked as a luxury feature. So what we have done is we have just attached two variables together, marking them as interaction variables. Then I am creating some aggregated features. So higher counts of premium features indicate more luxurious properties. So I have picked up all guest room, basement, air conditioning, hot water heating, preferred area. If it is yes, I'm just summing them up. And these are like additional features, right? These are luxurious facilities that you can get in a home. Then I have given weighted scores to prioritize more critical features, like guest room has been given a weightage of 2, basement has been given a weightage of 1.5, air conditioning as 1.5, hot water heating as 1, and preferenced area as a weightage of 3. This is another way of creating new features. I have gone ahead and created some composite features where the reason was the ratio captures here the ratio of the guest room and the basement. It captures whether guest rooms outnumber the basements or vice versa, which might reflect space utilization. Then interaction score for luxury features again, where this score quantifies the overall luxury appeal, means how much is the rating in the luxury appeal that I'm looking at of a house, combining key indicators like furnishing, location, and air conditioning. So I've got this. Then I can go with some interaction variables again, where I say that the luxury flag, if the guest room is yes and the preferred area is yes, then make that column a 1. Main road air conditioning flag means if the property is accessible at the main road and it does have an air conditioning, means both of them are yes, mark this column as a yes and convert it into a number, so it will become a 1. So these are a couple of features we created. You can go ahead and create multiple more features, and you can see that these variables are created here. So I have some numerical, some categorical. So I have created these values here. Now I'll start building the model again. So again, independent and dependent data set, create my dummies, split the data into train and test, and this time I'll go with linear regression model, the Scikit-learn model. I got my coefficients, the intercept and my coefficients, and these are all my coefficients that I have got. These are my, this is my intercept, and the equation that I'm getting is this entire big equation over here. This is the equation that you have got for linear regression with your feature engineered columns. Let us predict it. So I'm predicting on my train and the test set. And when I look at the R square, I see that my R square has significantly improved further. It has become 71% and 67%. Slight overfitting because the gap is around 3.5%, 4%. So there's a slight overfitting here. But overall, I see that the performance has improved when I went with feature engineering. When you look at the RMSE, the RMSE is still comparable. It is 0.20 approximately and 0.22. And now, since I've gone ahead and built all the 4 models, one with Scikit-learn with the simple target variable, Scikit-learn with normalized target variable, stats model with normalized target variable, and Scikit-learn with feature engineered columns. So I'm going to compare the results now. And I see that my maximum R square is in model 4, which is Scikit-learn with feature engineered columns. Slight overfitting, but for now we can accept it. And if you look at RMSE, that is also comparable. If you compare the results of Scikit-learn with stats model, you see that the R square for Scikit-learn and stats model are comparable. They are nearly similar, right? Not much of a difference. So either you do stats model or you do Scikit-learn model, both are going to give you same results. Feature engineering, again, it shows its importance that if I'm doing feature engineering and I'm using any of these models, stats model or Scikit-learn, my results will improve. Since we have built all the models and we are ready with my linear regression, now I'll go ahead and test the assumptions. So we are going to go with the 4th model, which is this one, Scikit-learn feature engineered model. And we are going to check for all the assumptions of linear regression. So let's see. So I'm doing the first test, which is the linearity test. So for linearity test, we go with the predicted values with my target variable. As we discussed in the theory, it should be horizontal and parallel to the x-axis. So if you look at this, I have gone ahead and done a residual plot where I'm using the model over here, which is your Scikit-learn model with feature engineered columns. And if you look at the red line, it is pretty much horizontal and close to 0. Slight pattern formation, but that is very less. So it is approximately linear. The second was normality of errors. When you look at the normality of errors and you plot a histogram of your errors, see histogram of your residuals means your errors, It is approximately normally distributed. Now, when you go for the third one, which is homoscedasticity, means constant variance of errors, here I am doing a White's test. White's test has a null hypothesis which says that the residuals are homoscedastic, and alternate which says the residuals are heteroscedastic. So if I look at the p-value of my heterogeneous White test, it shows me that my p-value is 0.90 or approximately 0.91. If it is 0.91, it means it is greater than 0.05, and I'll fail to reject my null hypothesis and I'll state that my residuals are homoscedastic. The fourth one is independence of errors from predictor variables. So here we have not done this. Just to understand the concept, what is Cook's distance? Cook's distance is going to help you identify which of your records or observations are controlling your errors, right? So if the Cook's distance is greater than 1 when we plot this, we remove such records from the data set and we rebuild the model. That is the solution to this in case I am getting Cook's distance greater than 1. Now, since all these models that we have built and we saw that we are getting decent results, and in the final model even, we see that we have met the assumptions of linear regression. What we'll do is we will go ahead and build this as my final model. And I will create a data frame with the coefficients. So I've just gone ahead and created the values that this is my intercept, this is the coefficient of area, this is the coefficient of bedrooms. So these are your x's and these are your beta coefficients. Some of them are very small, you see. Possibly it might have some 0, 0, 0, 0, 0, 1, 0, 2, but here it is showing as zeros. That is why you have minus and plus. So I've tried to filter them out over here. And still you have some of them because they might be very small and tiny going to the 8th or 10th or 12th decimal place. So you can consider them as 0 as well. So it is perfectly fine if you consider them as 0. But the primary purpose of me was to look at what are the values. So the intercept is 14.338, which represents the baseline log transform price of the property along with when the predictors are all 0. Area is this value, means larger the property, area positively influences the house price, which is pretty much expected. Bathrooms, it is 0.1834. So additional bathrooms significantly increase the house prices, reflecting the demand of convenience and luxury. Stories, the coefficient is 0.1062, which means that the properties with more stories are valued higher, indicating a preference of multi-story homes. Parking, you see the coefficient is 0.0536, means the parking availability positively influences property value. If the property is at the main road, the coefficient is 0.1027, means the proximity of the main roads increases house prices, likely due to better accessibility. If the preferred area is yes, the coefficient is minus 0.0109. This is unexpected, right? Because if it is in a preferred area, generally the prices increase. But if you look at what the data is telling me, it is giving me a negative relationship. And this is why I've written as unexpectedly being in a preferred area slightly reduces log transform price. This may indicate overpricing or saturation in these areas, possibly. If you look at furnishing status as unfurnished, the coefficient is minus 0.474, which means that unfurnished homes are less valuable compared to the semi-furnished or fully furnished homes. Guest room and basement, yes and no. This is a interaction variable we created. You see the feature turned out to be important now. A couple of other features also, you see. These are all features that we created, right? They have also become important. So this is what is the importance of feature engineering. Now coming back here, guest room and basement, yes, no, means the guest room is a yes and basement is a no. It is minus 0.0377, means homes with guest room but no basement detract values. Now, based on this, I can go ahead and build my recommendations where I can say that emphasize key features in marketing and pricing strategies. Highlight the properties with larger areas, more bathrooms, basements, and air conditioning in marketing materials. These features are strong drivers for house prices, as shown by the significant positive coefficients. For properties near main roads and in preferred areas, use premium pricing, as these interactions significantly enhance property value. Then the other one is optimize property listing for furnishing. So I can say that promote semi-furnished properties over unfurnished ones to attract higher bids. Semi-furnished homes add value and cater to buyers seeking partially ready-to-move homes. And consider offering furnishing packages or partnerships with furnishing companies to upsell unfurnished properties. Then address negative factors. Properties near main roads must not in preferred areas should be marketed with added value propositions such as soundproofing solutions, greenery, and enhanced community features to offset noise and traffic concerns. For unfurnished homes, consider adding essential furnishings to boost appeal and justify higher pricing. Then reassess investment in luxury features. So variables like luxury score and premium features have negligible or no impact on pricing. Avoid overinvesting in features that do not significantly influence buyer decisions and focus instead on practical high demand features such as parking, bathrooms, and basements. Enhance data-driven decisions for development and renovation. So invest in building homes with guest rooms and basements, as this combination yields higher prices. Properties with hot water heating and air conditioning should be prioritized for renovations. For new developments, aim to build properties in preferred areas with easy access to main roads, as these maximize buyer interest and willingness to pay. So this is pretty much in the case study where we have built the recommendation. So I'll collate all of it. The purpose was to predict price of home, which is a continuous variable. Hence we used linear regression. We built a Scikit-learn model with the original target variable. We saw that the R square was good and the RMSE was humongous. And this is why we went with the next model, which was again Scikit-learn model, where we had normalized the target variable by doing a log transformation. After this, we went with the stats model, and we saw that the Scikit-learn model and the stats model both were giving me the same result. In stats model, we did look at multi-collinearity. We also saw significance test. And at the end, we did some feature engineering and we tried the Scikit-learn model. After which, we did test the assumptions, build the results with the coefficients, and finally came up with our insights and recommendations. So that's all we have, everyone. Thank you for looking at this video. If you did like this video, please do like, share, and subscribe. And see you in the next video. Thank you.